A significant synoptic pattern is developing across North America, an amplifying upper-level trough over the eastern United States, a building ridge over the west, and the atmospheric dynamics support multiple winter weather events from Wednesday through the following weekend. Let me analyze the meteorological setup. The forcing mechanisms driving this pattern, the model solutions and their physical basis, and what the data tells us about snow potential for different regions. Starting with the large-scale pattern, we're transitioning from zonal flow to meridional flow. That means the jet stream is shifting from a primarily west to east orientation to a pattern with significant north-south components. The 500 millibar analysis for today shows relatively flat flow across the United States. Height contours run mostly west to east. The jet stream core is positioned across the southern tier. Wind speeds at the core reach 120 knots over the southern plains. By Wednesday, the pattern transforms. The 500 millibar heights show a deep trough over the east. The 540 decameter line dips from Canada down to Kentucky. That's a 600-meter drop in geopotential height over about 1,500 miles. Significant amplitude. At the same time, heights are rising over the west. The 570 line lifts from California up through British Columbia. The ridge is building. This dipole pattern, trough east ridge west, is driven by Rossby wave dynamics. When you have strong blocking in one region, it forces compensating troughs elsewhere. Right now, we're seeing high-latitude blocking develop near Alaska. That's forcing the ridge over western North America, which in turn forces the trough over the east. The jet stream responds to these height changes. Where heights are rising, the jet diverges. Where heights are falling, the jet converges. Convergence creates upward motion and supports storm development. Wednesday's jet stream analysis shows two relevant features. A jet streak exiting the Rockies with winds up to 130 knots, that's the northern branch of the jet, and a subtropical jet across the southern United States with core winds around 90 knots. Where these jets interact is critical for storm development. If they phase correctly, combining their energy, you get rapid cyclogenesis. If they don't phase, storms stay weaker. Current model guidance shows these jets approaching each other Wednesday into Thursday, but the timing of their interaction varies run to run. That's why we see such different solutions for coastal development. Let me examine the vorticity dynamics. Vorticity is a measure of rotation in the atmosphere. Positive vorticity advection, or PVA, is associated with rising motion and storm development. Wednesday morning, the 500 millibar vorticity analysis shows multiple maxima. There's a strong vorticity max, around 30 units of 10 to the minus 5 per second, diving through the northern plains. That's associated with the Alberta Clipper. A second vorticity max, about 20 units, is positioned over the Great Basin. That's energy that will dig through the Appalachians Wednesday night. By Wednesday evening, these vorticity maxima are moving into proximity. The northern max is over the Ohio Valley. The southern max is entering the Tennessee Valley. If they consolidate, merging into a single stronger feature, that supports stronger surface development. The European model at 6Z this morning shows them staying somewhat separate. The northern max moves through faster. By Thursday morning, it's already offshore. The southern max is still over the Appalachians, partial phase but not complete. The 0Z European from last night showed them coming together more completely. The vorticity fields merged over the mid-Atlantic Wednesday night. That created stronger PVA over the region and supported the slightly more robust coastal development that run showed. The GFS runs that showed major coastal storms had even better vorticity merging. The northern and southern maxima completely consolidated into a single feature with values exceeding 40 units. That strong PVA drove rapid surface cyclogenesis. Surface development is tied to these upper-level dynamics through the quasi-geostrophic omega equation. Without going into mathematical detail, regions of strong PVA and warm air advection support upward motion. Upward motion creates surface pressure falls. Pressure falls create or intensify surface low-pressure systems. Wednesday's pattern has PVA from the vorticity maxima. It also has cold air advection behind the system and warm air advection ahead of it. That temperature advection also contributes to vertical motion. The question is the magnitude and position of these forcing terms. Small changes in where the PVA maximum is positioned affect where the strongest surface pressure falls occur. That determines where surface lows develop. Currently, model consensus places the strongest PVA over the western Atlantic Wednesday night into Thursday. That's too far offshore to bring significant precipitation to the coast, but it's close enough that a 50-mile westward shift would change outcomes dramatically. Temperature structure is another critical factor. For snow, you need the entire atmospheric column to be at or below freezing, not just the surface, all the way up to where precipitation forms, around 15,000 to 20,000 feet. The GFS temperature cross-section for Wednesday shows the 0 degrees Celsius line at the surface extending from Louisiana through South Carolina. Aloft, the negative temperature contours slope inland. By 8,000 feet, the zero line is over Tennessee. By 15,000 feet, it's over Virginia. That sloping structure means precipitation that forms over Virginia falls through a freezing column and reaches the surface as snow. Precipitation that forms over the coast falls through a warmer column aloft and could start as rain before changing to snow. This thermal structure explains why mountains are favored for snow. Gatlinburg sits at 1,400 feet elevation. If precipitation falls there, it's entering the freezing layer 1,400 feet higher than Charlotte. Less warm air to pass through, higher chance of snow reaching the surface. For the coastal plain, the thermal structure is less favorable. Even with cold surface temperatures, there's warm air aloft. That can cause mixed precipitation or rain before transitioning to snow. The Buffkett soundings, forecast atmospheric profiles, show this clearly. The Wednesday evening sounding for Raleigh-Durham shows surface temperature at -2 Celsius. Cold enough for snow, but there's a layer from 3,000 to 6,000 feet with temperatures above zero. That's a warm nose. Precipitation falling through that warm layer melts. Even if it refreezes before reaching the surface, you get sleet or freezing rain instead of snow. Not ideal. The sounding for Asheville, in the mountains, shows a completely frozen profile. Temperatures below zero from surface to 20,000 feet. Any precipitation that falls there is snow. Moisture availability is the third key factor. You need moisture for precipitation. Sources for this system include the Great Lakes, the Gulf of Mexico, and Atlantic Ocean. The integrated water vapor analysis shows precipitable water values. Wednesday morning, values are around 1 inch across the southeast. That's moderate moisture for January. Not exceptional, but sufficient for decent precipitation if dynamics are right. As the coastal low develops Wednesday night, it can tap into Atlantic moisture. If positioned correctly, it pulls that moisture westward into the cold air. Values could increase to 1.5 inches along the immediate coast. But if the low is too far offshore, moisture stays over the ocean. The coastal plain sees minimal precipitation. Lake effect moisture is guaranteed for areas downwind of the Great Lakes. As northwest flow develops Wednesday into Friday, cold air moves over the relatively warm lake waters. That temperature difference creates instability, rising motion, snow bands. The temperature difference Wednesday between the lake water, around 38 degrees Fahrenheit, and the air at 850 millibars, around 10 degrees Fahrenheit, is about 30 degrees. That's sufficient for robust lake effect. Typical fetch calculations suggest snowbelt zones downwind of Lake Superior, Michigan, and Huron could see 8 to 16 inches in persistent bands. Some localized areas in the most persistent bands could exceed 20 inches. Now let's quantify snow potential using model snowfall output. The models run microphysics schemes that convert forecast liquid equivalent precipitation into snowfall using temperature-dependent ratios. The GFS accumulated snowfall for Wednesday through Thursday evening shows the Appalachian Mountains clearly. Purple shading, indicating 12+ inches, covers the Smokies and Blue Ridge above 3,000 feet. Lower elevations show gradients. Blue shading, 6 to 12 inches, extends down to about 2,000 feet. Green shading, 3 to 6 inches, covers elevations from 1,000 to 2,000 feet. The model is using snow-to-liquid ratios around 12 to 1 for the higher elevations based on the cold temperatures aloft. Lower elevations where temperatures are closer to freezing see ratios closer to 10:1. For the coastal plain, the GFS shows minimal snowfall on this run, an inch or less. The thermal structure doesn't support significant accumulation. The European snowfall output shows similar mountain focus. Heavy amounts above 3,000 feet, decreasing with lower elevation, minimal coastal impact. However, individual ensemble members show different solutions. I've examined the GEFS plume diagrams for snowfall at several locations. For Gatlinburg, the ensemble spread ranges from 2 inches to 18 inches. The ensemble mean is 8 inches. Widespread indicates high uncertainty driven by temperature and moisture variability across members. For Charlotte, the spread is even wider. 0 inches in many members to 12 inches in the most aggressive. Ensemble mean is 2 inches. That widespread reflects uncertainty in coastal storm development. For Philadelphia, the spread ranges from 0 to 15 inches. Ensemble mean is 3 inches. Similar coastal development uncertainty. The ensemble clustering analysis shows interesting patterns. About 30% of GEFS members cluster around a strong coastal development solution. These show significant snow for the mid-Atlantic and southern New England. About 40% cluster around a weak coastal development solution. Light snow or mix for interior areas, mainly rain or nothing for the coast. About 30% show offshore development with minimal impact. The European EPS shows similar clustering, slightly more members in the weak development cluster compared to GEFS. Slightly fewer in the strong development cluster. Probabilistic snowfall guidance combines these ensembles. For the Appalachian Mountains above 3,000 feet, probability of 6+ inches exceeds 70%. High confidence. For Gatlinburg, probability of 6+ inches is 35%. Moderate uncertainty. For Charlotte, probability of 6+ inches is 15%. Low confidence. For Philadelphia, probability of 6+ inches is 20%. Low confidence. These probabilities will evolve as model guidance converges or maintains spread. Beyond the first time frame, Friday through weekend shows continued troughing but weaker systems. The 500 millibar pattern maintains the trough over the east through January 22nd on current extended guidance. The GFS Week 2 outlook shows continued below normal temperatures. The ensemble mean temperature anomaly is -5 to -10 degrees Celsius across the eastern United States. That's significant sustained cold. Additional shortwaves rotate through the trough, Friday through the weekend. Each could bring light to moderate snow to portions of the region. Not major storms on current guidance, but winter weather nonetheless. The teleconnection patterns support this extended cold pattern. The PNA index is forecast to reach positive territory. The CPC, Climate Prediction Center, experimental forecast brings it to +1.5 by January 22nd. Positive PNA correlates with ridging over western North America and troughing over the east. Statistical composites of past positive PNA winters show this correlation. The NAO is forecast to go negative, -1.2 by January 20th on the CPC forecast. Negative NAO supports high latitude blocking and eastern troughing. The AO is also forecast negative, -1.8 by January 20th. Negative AO allows Arctic air to escape the polar region more easily. These are not deterministic predictions. Teleconnection forecasts have skill limitations beyond 1 week, but they provide context for the pattern evolution. Current satellite observations show the pattern transition beginning. Water vapor imagery shows the trough digging over the Rockies. Dry slots wrapping around the backside of the building ridge over the Pacific Northwest. Upper air observations from Rawinson launches across western Canada show Arctic air in place. The 850 millibar temperature from Edmonton this morning was -28 Celsius. That's the cold air source moving south next week. Surface observations show the Arctic high building. Pressure at Bismarck is 1,018 millibars and rising. That high will push south and east, driving the cold air into the United States. Preparation should focus on confident aspects of the forecast. Cold is certain. Temperature guidance shows excellent model agreement. Expect the coldest air of the winter Wednesday through the following week. Mountain snow is likely. All models agree on significant accumulation above 3,000 feet Wednesday into Thursday. Prepare accordingly if you live in or plan to travel to these areas. Coastal storm details remain uncertain. Model and ensemble spread is large. Outcomes range from significant to minimal. Monitor forecasts as guidance evolves over the next 2 days. Lake effect snow is likely for typical snowbelt zones. Northwest flow Wednesday through Friday supports this. Expect accumulating snow in usual locations downwind of the Great Lakes. Updates continue as new model data arrives and the forecast picture clarifies or remains uncertain.